Okay. Once again, good afternoon to all my dear students and all the viewers. Today, on the same power station engineering, today's topic was thermal power plant. In my next session, lecture 2, I will solve some numerical problems and we will also discuss about Rankine cycles and its performance. As you know, this is the thermodynamic cycle of the steam power plant, and in your syllabus you have to explain this cycle with the help of pressure volume diagram, temperature entropy diagram and enthalpy entropy diagram. In three diagrams, by the help of these three diagrams, you have to explain the whole process. So, first this is the temperature entropy diagram of the Rankine cycle. This one is your all processes are shown internally reversible. That means it is the ideal cycle. Ideal cycle. There is no pressure drop or no heat loss anywhere. It is the ideal cycle. From the ideal cycle, we will start covering. Then this is the temperature entropy diagram. In the y-axis is the temperature. So it should be in Kelvin, degree Kelvin, and entropy in your SI system, you know, unit is kilojoule per kg per Kelvin. This is the unit of the entropy, specific entropy. So you know 1, 2 is your pump work, H1, H2 your pump work, and 2, 3 is your heat addition in boiler at constant pressure. At boiler pressure is the heat transfer is H3 minus H2, and the turbine work is expansion of the turbine. In here is the arrow diagram 3 to 4. 3 to 4 is the turbine work done. It is in the TS diagram. I will explain how we are getting turbine work done as S3 minus H4, heat addition in boiler is equal to S3 minus H2, and mainly these two things, and pump work is WP pump work is equal to H1 minus H2, H2 minus H1, and heat rejected in condenser QK is equal to H4 minus H1. This is the formula for calculation of Rankine cycle performance, study of Rankine cycle. We will discuss this derivation. Now, this same cycle is plotted in PV diagram, PV plane, pressure, here pressure is in the y-axis and volume in x-axis. You know pressure unit is bar, and the volume unit is meter cube per kg, specific volume. And already I told this is your saturation line, saturation liquid line, there it is saturation vapor line, and this is the critical point. where liquid line and vapor line coincides. This is known as critical point or critical pressure. This is the corresponding pressure is critical pressure. Here in the pump, the condenser pressure is increased to boiler pressure. This is your condenser pressure or this is condenser pressure, this is your boiler pressure or turbine pressure, turbine inlet pressure, inlet. This is turbine PK condenser pressure, or it is also known as turbine outlet pressure, turbine outlet pressure. That means expansion takes place. This is the expansion method. You know, this is a 3, this is the V3, this is V4. Here V4 is greater than V3. That means it is expansion process. Volume is more. Final volume is more than initial volume. So this is the expansion process. This takes place in the turbine. And in the constant pressure, your heat rejection takes place in the condenser. This is the condenser. It is heat rejection. Heat goes out. Heat out. Clear? So this is one. Now your enthalpy entropy diagram is in the this slide. What tell you? This is your enthalpy entropy diagram of Rankine cycle. Same cycle, it is explained. This is also your Rankine cycle. Rankine cycle, you say the ideal cycle explained in HS diagram, enthalpy entropy diagram. This is your, you can call as specific enthalpy or specific enthalpy and specific entropy. Diagram. This can also be called as, known as Mollier diagram. Mollier diagram or chart. Mollier chart, popularly known as Mollier chart of, it is found in your steam table. This chart is also found in steam table book. जो बहीटार steam table बहीटा ता भीतर देखो ये Mollier chart टा थिबो. तादेरु तमे सब डायरेक्ट एंथैल्पी पाइबो at any point. It is very helpful. This HS diagram is very helpful for calculation of different parameters, different performance of or different value. This turbine, this is the pump work. This you can get directly. Here it is H2. You will get direct value from the Mollier diagram. H2, H1, this is H3. This directly you can get H3 here. No calculation. You get directly from H4. You can get H4. This is the y-axis. It is, and its unit is kilojoule by kg. And its unit is kilojoule per kg per Kelvin. So here this chart is very much helpful for calculation of solution of numerical problems. So this Rankine cycle is given in this plane. This is the pump work and H2 to H3. This is the H2 H3 to this H2. it is your boiler heat input in boiler, and work done is S3 Wt is here. You can directly get Wt is equal to S3 minus H4. So this diagram, by this diagram you will get within very few minutes you can able to solve the problem from this molecular chart. This is the your Rankine cycle 1, 2, 3, 4, 1. This is a full cycle. This is your condensation. देखो how the heat is rejected. एटी H2 रे थिला H1 को कमिला माने एटा रिड्यूस हला heat rejection हला just so it is downward line, downward decrease this process is direction is forward but it is downward, this is incline downwards. So that means heat rejection takes place. And here you know turbine always a isentropic process, reversible adiabatic process. So work done is this difference S3 minus H4. You can get directly. So you can get the efficiency of the plant or cycle as the net work done. That's mean turbine minus pump work divided by heat input in boiler. That means S2 minus turbine work is S3 minus H4 minus pump work. Pump work is W2 minus W1, S2 minus H1 minus H2 minus H1 pump work, and the boiler input is heat input is S3 minus S2 S3 minus H2. So from this molecular diagram you can without the help of the steam table, एठी स्टीम टेबल तुम दरकार हेनी तो मोलियर चार्ट देखिए बही रे अच्छी तादर तुम एटा प्लॉट कर माने केमती प्लॉट करियो ना प्रेशर दीटा दिया हेतिबो प्रेशर लाइन थिबो सेटा प्लॉट करी तुम पाई जिवो. So this is one direct calculation without any help of steam table. Next we will derive how it is this formula we get. We derive that. That derivation is given here. This. The performance of Rankine cycle. From definition of heat in cycle, which is also Rankine cycle, the definition of Rankine efficiency is the ratio between net work output to heat supply. Now let us take for derivation, let us take small h is the specific enthalpy in kilojoule per kg, and s, this is small s, specific entropy in kilojoule per kg per Kelvin. T is the absolute temperature in degree Kelvin. Next, Rankine efficiency आमे जानिले, this is the formula Wt minus Wp divided by heat input in boiler. I already told. Wt is the work done by turbine, Wp is the work input to pump or work supplied to pump, and Q boiler heat input to the boiler. The above physical quantity can be derived by using steady state energy equation. You know steady state energy equation or steady flow energy equation. The full form of SSEE is steady state energy equation. or also known as steady flow energy equation. Steady flow energy equation. Steady flow energy equation. This equation is applicable for open system. All the components in the Rankine cycle, that is boiler, turbine, condenser, and a pump, the main 4 components all are comes under open system. That means mass and heat both transfer across the boundary. So this equation you can apply for each boiler, turbine, condenser, pump. So that equation I have given here for m quantity of mass flow. H1 is the enthalpy, m next is your kinetic energy, half mv square, and it is potential energy, and it is heat transfer, this is work transfer, this is in the outlet point, one is the inlet, another is outlet. Suppose this is your turbine. So this is your I and this is out, O. Inlet, outlet. So you can say inlet as a 1, outlet as 2 section. This is the turbine. You know turbine कौन हुए ना, expansion takes place. So it is the expansion, area increases. So total energy at inlet is equal to total energy at outlet. This is the known as steady state energy. In the for m, if it is m is 1 kg, if you take, if OF has 1 kg, this is the simplified equation for 1 kg, where m is 1, H1 plus V1 square by 2 GZ1 plus Q specific heat, specific war in outlet. This W can be here, so we are taken for that. So this is, now apply this to boiler. Now this is say your you will apply for boiler. कौन सा? Now this steady state equation, enthalpy at 1, kinetic energy 1, potential energy 1, and heat transfer at section 1, W can be come to this place also, minus take for left side. So total energy here is equal to total energy output here, conservation of energy, that equation. Now for boiler, suppose this is the boiler. In boiler, suppose this is 1, this is 2, but actually that is point in the boiler is 2, 3. 2, 3 process in the boiler. We are saying 2, 3. So let us take 2, 3. This is point 2, inlet of the boiler, outlet of the boiler. Here you apply the steady state energy equation. It is H2 plus V2 square by 2 plus GZ1 plus Q minus W is equal to H1 H3 plus V3 square by 2 plus GZ2 this much. So here velocity, you know, that is same, V2 is equal to V3, because there is no such that velocity increases. Here kinetic energy at inlet is equal to kinetic energy outlet, because it is not any moving parts is there, it is only a heat transfer unit, boiler, and their elevation is also same, Z2 is equal to Z3. And so what will happen na, also W is 0, there is no work here, boiler that kichhi kamo hueni, only heat transfer takes place. So then W is 0, ta mane ye 0 hela, ye kati gala, Z0 kati gala, ke rohila finally H2 is equal to H2 plus Q is equal to H3. So Q is equal to H3 minus H2. Okay, so this is the heat input in the cycle, in the boiler. Similarly, you can solve for turbine. Suppose now this is a turbine. In turbine, what are the states? 3, 4. 3 is the inlet, 4 is the outlet. This is 3, this is 4. As per our cycle, this is the steam turbine. Okay. See, then you apply the steady state energy equation, this one. S3, I am writing here. S3, I am writing here. S3 plus V3 square by 2 plus GZ3, Z3 is elevation, potential energy in the height, Z3 elevation, and Q is same, Q